Nvidia's GPUs, when they say our GPUs, people imagine little GPUs. Our GPUs, one GPU is now rack scale. It's 2 tons, 120,000 watts, about $3 million. That's a GPU. We also sell smaller GPUs, the ones that Geoff Hinton used. I went to universities everywhere, and we meet with researchers, and that initiative of getting CUDA into higher education and researchers everywhere caused some researchers to reach out to us in 2012, 2011. And Geoff Hinton was trying to solve computer vision. And Andrew Ng was trying to solve computer vision.
Please join me in welcoming Jenson Haung.
Oh, thank you. It's nice to wake up this way.
Well, you've been working for hours.
Yes, I have.
Eyes on it. What was the edge to make Nvidia the center of this revolution?
Yeah, two serendipitous, two serendipitous moments, and then one which is just a great, again, first principle observation about deep learning. The serendipity started with, I was trying to solve computer vision. And we wanted to solve computer vision for a lot of different reasons. Whether, well, anyways, we want to solve computer vision. And computer vision was really brittle, really hard to generalize, a collection of a whole bunch of tricks, and I really hated how the industry was evolving, and we're really quite frustrated with the progress. Meanwhile, one of our major strategies of democratizing the architecture is to get scientists in higher education to use our platform, use CUDA. And so I started with seismic processing, molecular dynamics, particle physics, quantum chemistry. I took Nvidia CUDA everywhere, and actually there was a strategy at the company called CUDA everywhere. That meant Jenson schlepping CUDA all over the world. And so I went to universities everywhere, and we meet with researchers, and that initiative of getting CUDA into higher education and researchers everywhere caused some researchers to reach out to us in 2012, 2011. And Geoff Hinton was trying to solve computer vision. And Andrew Ng was trying to solve computer vision. And Yann LeCun was trying to solve computer vision because there was a contest coming up called ImageNet that Feifei's in charge of. And I was trying to solve computer vision. And so when you're naturally trying to solve a problem and then all of these interesting people are solving similar problems, they attract your attention. So that's serendipity. The thing that was great observation is that we could create a new type of solver for them that's called cuDNN, kind of like the sequel of in-storage computing. We invented cuDNN, which is in-network computing, if you will. And that way of doing computation, this library called cuDNN, made it possible for all of them to use CUDA successfully. But the thing that was I saw the same results as everybody else. Everybody saw the big jump in computer vision effectiveness. But where we took it further was we reasoned about, so this is so good at computer vision, and why, and what else could it be good at? And the ability for deep neural networks to be extremely deep, meaning because each layer is trained independently of the others. And you could backpropagate from a loss function all the way back to its input. You could learn almost any function. And we came to the conclusion, this is a universal function approximator. And if we can then add to its state, which is, CNN was a kind of a two-dimensional, multi-dimensional pattern recognizer, and then RNNs gave you a state machine within it, and LSTM gives you an even better state machine, and then transformers give you the ultimate state machine. And so the idea that we would have a universal function approximator that can learn almost any function, well, the question is what problem can it solve? Now you invert the question, and we came to the conclusion most of the problems we wanted to solve could have a deep learning component to it. And so we decided, how would we reason about where deep learning could be 10 years from now, 20 years from now? We broke down the computation problem, and we came to the conclusion that every single chip, every single system, every software, every single layer of the computing stack could be reinvented. And that decision to go after it was probably one of the better decisions in history.
This is where the legend of Nvidia truly begins. A company born not from luck, but relentless curiosity. When computer vision was broken and fragile, Nvidia turned frustration into innovation. CUDA wasn't just software, it became the language of intelligence. By spreading it through universities and labs worldwide, Nvidia unknowingly united the world's brightest minds. Hinton, LeCun, and Haung all converged on the same mission, and Nvidia gave them the power to achieve it. That's when the spark of deep learning ignited, proving that every chip, every layer, could be reinvented to solve the impossible.
I was doing AI research at the time at Stanford, and the major constraint was always the compute.
Yeah.
We had limited clusters in order to run these algorithms, and NVIDIA came in and not only relaxed that compute, but made it possible with the CUDA infrastructure.
Yeah.
And that is largely your history. You make more and more compute possible. In 2016, you very famously created the world's first AI factory, the DGX-1.
Yeah.
You actually hand-delivered it to Elon Musk at OpenAI
Well, I built this brand new computer, and it doesn't look like anything the world's ever seen before. It doesn't work like anything the world's ever seen before. And I remember announcing it at GTC, and literally the audience was just like this. Nobody knew what I was talking about. And that was a joke. And so with the same amount of applause. And so I announced this thing, and everybody goes, uh-huh. And literally on that GTC, I invited Elon to talk about the two of us were working on self-driving cars, and so he came on stage and he says, Jenson, what's that computer? And I said, DGX-1, and I built it for this reason. And he goes, I could use one. And I finally got a PO. And then he goes, yeah, I have this nonprofit. And I said, when you build something brand new, the last thing you want to hear is that your first customer is a nonprofit. And so anyhow, I delivered. I was the DoorDash computer guy, and I DoorDashed this computer up to San Francisco, and the company was OpenAI.
It is a very profitable nonprofit, or revenue scale nonprofit.
No, we've been working together for a long time. Every model has been built on NVIDIA since, yeah.
And this thing is huge. Physically, when Jenson's talking about a computer, we're talking about a massive device.
NVIDIA's GPUs, when they say our GPUs, people imagine little GPUs. Our GPUs, one GPU is now rack scale. It's 2 tons, 120,000 watts, about $3 million. That's a GPU. We also sell smaller GPUs, the ones that Geoff Hinton used. That's like $1,000, $500 that plugs into your PC. And you could use it for video games or AI and things like that. But we also have bigger GPUs. And then a 1 gigawatt AI factory GPU is about $50 billion.
So tell us about these AI factories, because you might have the small one, might be the AI blender, but then you have the really big one, these AI factories that you went all in 2016 and started to say the world is going to need AI factories. How did you get that edge, that conviction? And then
you just got to reason about it. Exactly, you got to reason about it. So we built the first one, DGX-1. It was the most expensive computer the world's ever seen, $300,000 per node. And it wasn't that successful. And so I came to the conclusion we didn't make it big enough. And so we made a bigger one. And the second one became super successful. And now the question then becomes, how large do you make it, and how hard do you drive computation? The reason why things are moving so fast is NVIDIA's product cycles and the way we innovate, the way we design. We're not designing a chip. We're designing an entire infrastructure all at one time. We're the only company in the world today that you can give a building, some power, and a blank sheet of paper, and we can create everything within it. All of the networking, all the switches, all the CPUs, all the GPUs, all of the technology within that entire factory we can build. And and it all runs the same software stack from Nvidia. And because we can integrate like that, we can also move extremely fast. So I could redesign the next years, and every single year they're all software compatible. The benefit of software compatibility is velocity. The reason why the PC was able to move so fast was because they were all Windows compatible. And therefore, by definition, if you're compliant with the stack, you could build chips as fast as you like. And so we're now building AI factories as fast as we like, at the limits of what's physically possible. And so, and because we're innovating at such incredible scale, and we're co-designing, meaning we're changing algorithms, we're changing software, we're changing networking and CPUs and GPUs all at the same time, we break out of Moore's law's limits, which is, as you know, slowing down. And so generationally, we introduce performance levels by about 10 times. I mean, it's an incredible level of performance that we give to the market every single year. The reason why we do that is we believe that just around the horizon is a problem that is so large you need a larger computer, faster computer, on the one hand. On the other hand, when we increase performance at the same power, we're decreasing your cost. And so we're driving costs down incredibly fast, which allows customers to do bigger things, which allows them to generate more revenues from the same factory. And so NVIDIA's adoption today is because we are both the highest performance, we're the highest scale, and so if you want giant systems, you could do so, and we're the lowest cost. Our performance is so high, for example, if your data center is 1 gigawatt, you're not going to get more than that. You're 1 gigawatt. And so if our perf per watt, our energy performance per unit of energy used is 3 times, your company can generate 3 times more revenues in that factory. That's why I call it a factory. It's not a data center, it's a factory. They're making money from it. And so these AI factories wants to keep driving the scale up. They want to keep driving the revenues up. They want to keep driving the throughput up. And so that's the reason why we're innovating so fast. And it's hard to keep up with us. And it also explains why we're successful.
Then came the moment that changed everything, the creation of the world's first AI factory, the DGX-1. Jenson Haung didn't just build a machine, he built the heart of modern AI. Hand-delivered to Elon Musk and OpenAI, it marked the start of an unstoppable era. Nvidia stopped designing chips. They started designing entire universes of computation. From rack-scale GPUs to billion-dollar AI factories, each one more powerful than the last. Breaking Moore's law, accelerating discovery, and transforming data centers into profit engines, Nvidia isn't following the future, they're building it. Don't forget to like, subscribe, and stay tuned. The AI revolution has only just begun.